Hello, this video covers section 13.1, Permutations and Combinations. At the end of the section, hopefully we can solve problems related to the basic counting principle, distinguish between dependent and independent events, and solve problems involving permutations or combinations. So let's begin. Our first problem goes as this. Chelsea is deciding what meal to prepare for dinner. She needs to choose a meat, a starch, a vegetable, and a dessert. For a meat, she can choose from beef, chicken, or fish. For a starch, she may select potato or rice. And for a vegetable, she can choose broccoli, string beans, and asparagus. Isn't she lucky? Delicious. Her dessert choices, oh, it gets better. Her dessert choices are apple pie, peach pie, or blueberry pie. If it was me, there's only one choice, apple pie. Gotta love that. So as we look at all of these choices, this wealth of things she can choose from, are the choices for each category of food independent or dependent events? So for instance, if she chooses beef for her meat, does that impact her starch choice or her vegetable or her dessert? Does that have any impact what she chose for meat? Well, no, it doesn't. The choice of one type of food does not affect the choice of another type of food. So we say the events are independent. Okay, that's the key thing. Since they don't impact each other, we say they're independent. The other choice would be if they do impact one another, we say they are dependent. So how many different ways can Chelsea choose the foods for her meal? Okay, well, she has 3 choices for the meat, 2 choices for the starch, 3 choices for a vegetable, and 3 choices for a dessert. So here's a little table outlining each of those. And we can quickly do multiplication to solve this, saying that she has 3 choices by 2 choices by 3 choices by 3 choices, which gives us 54 different meal choices. She is set. I hope she can make her mind up. She'll be there for a while. It's like me at a buffet. Just can't choose. Hold up the whole line. She has 54 different meal choices from just those 3 meats, the 2 starches, 3 vegetables, and 3 desserts. We can multiply them together because they are independent of one another. So the next section we're going to handle gets a little bit more involved. It's a concept called permutations. That last one used the basic counting principle. Now we're moving into permutations, and there's 2 types of formulas that we'll have, so you may want to go ahead and jot them down. If you need to pause the video, you can. The first one is when we have the number of permutations of n objects taken n at a time. We have this formula that says P of n is n factorial. We've talked about how to calculate factorials. The other one is where the n value, the number of objects taken, does not match the how many are taken at a time. So for instance, if we have n objects that are taken r at a time, so 5 objects that we take 3 at a time, we call those P of nr, where we have n factorial over n minus r factorial. Now here's the catch, and you'll see how this works out in a little bit when we use the formula, but these 2 formulas really are the same, and I want to highlight that. Because if n and r have the same value, this formula becomes n factorial over n minus r factorial. However, if r is actually the same as n, so let me pull this r out and I'll put another n in here. This becomes n factorial over 0 factorial. Now this is one of those weird things with factorials that by the definition 0 factorial is 1 by definition. So this ends up giving us n factorial. So if I had to memorize only one formula to use all the time, it would be this formula. Just remember, n objects taken r ways, and you can use this formula no matter what if you remember this. Also remember this little property about factorials. All right, so for example 2, 4 ice skaters, Allison, Francesca, Madison, and Alexa are skating in a competition. First question is, are the selections of skaters to perform first, second, third, and fourth independent or dependent events? Okay, so the thought here is that the choice of the skater to perform first does not affect the choice of the skater to perform second, third, fourth. Therefore, it does affect. So the events are dependent. Because if I choose, say, Allison first, that means she can't be chosen second. So it did impact the second choice. She also couldn't be taken third, so it impacted the third choice. It impacted all the choices after that. So they are dependent because of the fact that one choice impacts the others. I'm sorry. Assuming that no two skaters may perform at the same time, how many ways can the skaters be arranged to perform? So since order is important, one's happening after another, it's not all at the same time, we call this a permutation. Okay? So the first method gets kind of messy, but it's a tree diagram. And I'll zoom in on this, but the thought process is there are 4 possibilities for the first performer, 3 for the second, because one of them is already gone, 2 for the third, and 1 for the fourth. And we look at this diagram here, we can get a little bit more detail. And I'll zoom in to show you exactly what happens. So the thought is I list everybody that could go first. Allison, Francesca, Madison, Victoria. And let me zoom in and I'll show you what I mean. So here we have everybody that could go first. Allison, Francesca, Madison, and Victoria. Then the next column I list what would happen if Allison went first, then second, Francesca, Madison, or Victoria would go. Likewise, if Francesca went first, then that leaves Allison, Madison, or Victoria to go second. And I continue on listing for Madison going first or Victoria going first, what would be the outcomes for the second person going. And then I continue that pattern for the third person. So if Allison went first and Francesca went second, that leaves a choice of Madison or Victoria to go third. And likewise, if Allison went first, Madison went second, then Francesca or Victoria would go third. And then whoever's left would have to go fourth, so that's who I put in this final column. Counting up every one of these final possibilities, so every one of these branches, there are 24 possible ways for this to happen. But goodness gracious, is that ever tedious to list this out in a tree diagram? So there must be a better way to do this, right? Well, and that's where the formula comes in. This situation depicts 4 objects taken 4 at a time. So there's 4 skaters that I'm choosing. 4 of them, they're each going to get thrown into a slot. First, second, third, fourth place. So this is a case where my n and r values are the same. So it's a simple case of just doing n factorial, which comes out as 4 times 3 times 2 times 1, or 24. Boy, is that a lot nicer, neater, and cleaner. Math rocks again, making things cleaner. So there's 24 ways we could put the skaters to perform. Let's go to another one. In a baseball game, 9 players on a team may play the field during any given inning. Assume the same 9 players play during the entire game, so we don't substitute anybody out. How many different ways can the coach arrange the batting order? All right, so since order is important, the situation is a permutation. Okay. Also, the 9 players are being taken all at once, so the situation can be represented as P of 9, 9. So R and N are the same again. A nice clean problem, P of 9, 9 equals 9 factorial. So we get this whole big 362,880. Could you imagine the size of that tree diagram? That'd be mind-boggling. That'd be huge. So this is definitely a better way to do it. All right. Now, the second part, in how many ways can the coach select who will play the outfield positions? That is left field, center field, and right field. So there's 3 positions. So this becomes a little bit different. I'm not choosing the same situation here. We have 9 people being chosen 3 at a time, a group of 3 being taken out of those 9. Again, order is important, so it's still a permutation, but here n and r are not the same. This is p of n3, so n is 9, r is 3. So I use that second formula where it's 9 factorial over 9 minus 3 factorial, which simplifies out to 504. So there's 504 ways we can arrange those 3 positions on the outfield. So all of the aforementioned situations were permutations because order was a consideration. One pick impacted the others. The next scenarios are combinations due to order not being consideration. One pick doesn't impact the next pick. Okay? Kind of like a lock or combination lock. You can have the same number twice in a row on the combination locks. Okay? So your combination might be 12, 5, 5. You could have that happen. Just because I chose 5 once doesn't impact the next number. So here's our formula for combinations. The number of combinations of n objects taken r at a time is defined by C of nr equals n factorial over n minus r factorial times r factorial. So here's our example, cinematography. In 1998, 195 theatrical films were released in the United States. Of these, only 5 were nominated for the Academy Award for Best Picture. How many groups of 5 movies could have been chosen to be nominated for Best Picture? Since order is not important, the selection is a combination of 195 movies selected 5 at a time. It can be represented as C of 195, 5. So I just plug them into the formula and boom, 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 boom. Got all the simplification. You need to write it down. You can pause. But we get an astronomically large possible way we could combine them. That's wild. All right. So let's keep moving. At Kennedy High School, there are 12 names on the ballot for sophomore class officers. 6 will be selected to form a class committee. How many different committees of 6 can be formed? Okay. So order is not important in this situation. So the selection of a combination of 12 people chosen 6 at a time. Okay, so here we go. C of 12, 6. We get 12 factorial over 12 minus 6 factorial. Then we have 6 factorial. Here we go. We get 924 is our total. Okay. Let's keep going. Part B, in how many ways can a committee of 6 be formed if each student has a different responsibility? Okay. So, order has to be considered in this situation because each committee member has a different responsibility. So it matters when they're chosen because they have a specific responsibility. So now this is a permutation, not a combination, because order matters. So I use my permutation formula of 6 people chosen from a group of 12. So here we go. We get 665,280. And our last bit here says, if there are 7 girls and 5 boys on the ballot, how many committees of 3 girls and 3 boys can be formed? Oh boy. So now we're going to throw in our counting principle for these 2 events. Order is not important because we're not assigning roles or anything. There are 3 questions to consider. How many ways can 3 boys be chosen from 5? And how many ways can 3 girls be chosen from 7? Then how many ways can 3 boys and 3 girls be chosen together? All right, since the events are independent, the answer is the product of the combinations. So I'm going to take the combinations for the boys and the combination for the girls, and then I multiply those possibilities together. So here's my combination for the boys, combination for the girls. All right. So this is what we get. Here's my combinations formula. All right. So I get 350 altogether. All right. 350 possible committees. I personally, if rewriting this one out, I probably would have jumped down to this part right here, from here, this being my combination formula for the boys, this being the combination formula for the girls, with n minus r being the 2 factorial, and n minus r for this, 7 minus 3 being my 4 factorial. Okay? So that is the video on permutations and combinations and the basic counting principle. Be sure to do your assignment, practice, 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 and hey, you get really good at this stuff. It'll help you figure out your odds and probability in Vegas. All right, have a good one.